So in the last two lessons you've been learning about what are called saturated hydrocarbons. Those are hydrocarbons which have got no double bonds, no triple bonds. You can't add any more hydrogen atoms to them. They're saturated. The ones we're going to learn about today, tomorrow, and probably we'll get onto alkenes on Friday. So the ones we're going to go ahead to look at are the unsaturated hydrocarbons. What that means is that you can add more hydrogens to it by breaking some of the carbon-carbon bonds. So going from a double bond to a single bond. And we'll look at that when we look at the reactions of these tomorrow. So now that we've got things that have actually got something different to alkanes, we are going to identify what the functional group is. Functional means what makes it function the way it does, what gives it the chemical and physical properties that it's got. That's why they're called functional groups. There's quite a few of them to learn this year. The first one you're meeting is the carbon-carbon double bond. If you see a carbon-carbon double bond, it means you have an alkene. And you also can check the general formula to see if they are non-cyclics or cyclics. Alright, so cyclohexene, which is a 6-carbon ring with one double bond in it, is C6H10. It's actually got CnH2n minus 2. If it was just hexene though, so not cyclic, it would be C6H12. Alright? So these are things we need to check. As I say, we'll look at the properties and chemical reactions tomorrow. All I want to go through is the naming and the isomers and stuff like that. There's a bit more happening with these. You don't just have the structural isomers. There's a thing called geometric isomerism as well. Geometric, like geometry and maths, means how are things laid out in space. So they actually have the same structural formula, which we're going to see, but they have different arrangements of the atoms in space. They're actually arranged differently, and that can't be changed. And that's why you've got the molecular models in front of you, so you can make these as I go through them to see actually that I am telling the truth. Okay, so let's go through the naming, and that'll lead us into isomerism over here. So, just like in the alkanes, we use that same naming, meth, eth, prot, bute. However, of course you can't have an alkene with only one carbon in it, because it needs a carbon-to-carbon double bond. So the smallest of the alkenes is ethene. So again, if I go through those steps, if I was to look at the formula for this thing, it's CnH2n, so it's either a cyclic alkane, well it can't be if it's only got 2 carbons, or it's a non-cyclic alkene, and that's what it's going to be. So I automatically write my carbon next to my carbon with an equal sign between it to show a double bond. Then I fill it in and go, oh yep, that fills in all the hydrogens there, that's everything. Again, I would name these backwards. So it's got a double bond, so it ends in the suffix ene for alkene. And then it's only got 2 carbons, so meth, eth, it must be ethene. Alright? Doesn't need any numbers or anything like that because there's no other arrangement of this that can exist. What I've got in brackets, or in this bubble here, is this is how I show the abbreviated or the shortened or the condensed structural formula. So this is showing every atom and every bond, so it's the structural formula, but actually this is all you really need to write in your exams. Shows the double bond, alright, and it's quite obvious that CH bonds are going to be single bonds, so you don't really need to show that. Alright, let's add a carbon to it and see what happens. So if we have C3H6, again, that's CnH2n, so I know that it's going to be linear. So I put the carbon-carbon double bond, then I put another carbon on the end of it. And then I just fill it in with all the hydrogens. Again, you'll see that I've shortened this to being CH2, then a double bond, CH, single bond, CH3. So it's showing the structure, but it's a lot more condensed. The name for this one, again, it's got a double bond in it, so it must end in ene. It's got 3 carbons, so meth, eth, prot, it's propene. Now if I was to move that double bond to there, it's the same molecule. I'm just looking at it from the other side of the board, as it were. So I don't need to put any numbers next to this. That's its name. All right. Technically, you could say it's number 1. It's 1 propene because the double bond is between the 1 and the 2. 1's a smaller number than 2. So technically, you could call it 1 propene, but you don't need to, because if we move the double bond, it's still the same structure, still the same compound. Things get a bit more interesting when we get up to C4H8. There's actually 4 isomers of this that are alkenes. Then you chuck in the cycloalkanes as well, and there's even more. So I'm going to go through them, starting with these two because they just show structural isomerism, and then I'm going to swap the boards over so we can see one that shows geometric isomerism. Even though they have the same structural formula, their geometric description is different because their actual 3D structure is different. So when you make them with models, they look a bit different. So let's just go through this. What I've done in the bubbles, I've given you the condensed structural formula because that'll actually make it a lot easier for us to name it. So this funny looking thing here actually is CH2, CH, CH2, CH3. It's got a double bond in it, so it's got to be an alkene, so it ends in E and E. Now, here's where things get a little bit more interesting. Remember in the alkanes, we numbered any long carbon chain backwards and forwards. Okay, so we go 1, 2, 3, 4 this way, and we number it backwards as well. What we need to do is find the lowest number that has got the alkene on it, and that is number 1. So we're going to put a 1 before the ene. That says where that functional group is. And then we're going to count, yep, there are 4, so meth, eth, prop, bute, so it's bute 1 ene. This one here is a little bit different. I'll stop this video and we'll start it again, going through this one and the others. This one here is quite different. Now actually I've not really drawn it the easiest way for you to see its condensed formula, so I'm going to show you that I've actually done it backwards. I've written it as CH2C, then bracket CH32. That looks a bit weird. That's not really what that looks like. But actually if I show you going backwards, you'll see how that was formed. Here's our CH2, here's our double bond, here's our carbon that's got no hydrogens on it, and these two are both CH3, coming off that one carbon. So because they come off the same carbon, I write it as CH3 with a little 2 next to it. Alright, so hopefully that makes a bit of sense with that one. Now my trick here is to look for the longest carbon chain that I can find that has the double bond in it. I'll say that again. Look for the longest carbon chain you can find that has the double bond in it. And it's either this one here or this one here. Both are equally the same length. They both have 3 carbons. I'm going to choose the top one just for simplicity. And again, I'm going to number it. Alright? Now, if I have a look at that, the alkene is either between 2 and 3 or between 1 and 2. Well, 1's the lowest number out of all of those, so I'm going to choose that it is a 1-ene. Alright? So it's something or other 1-ene. It's got 3 carbons in its longest chain, so it's prop 1-ene. Okay. And then I've got a side chain here that is made up of 1 carbon, so it's methyl. And technically it's 2 methyl prop 1-ene. Now actually, if I was to move that double bond to there, notice that's on carbon number 1 as well. So now that I've tried putting the double bond the only other place it can go, and I see I make the same thing, I can get rid of that number. It's not actually needed. So I'm going to just call it methyl propane. Because if I was to move the double bond anywhere else, it ends up making the same compound anyway. So I don't need any numbers. If you move the functional group and it doesn't change the structure, you don't need the numbers. They're not required. Okay? So I initially put it in, just from habit, more than anything. I initially put it in and then I take it out if it's not needed. Okay. Rightio, I'm going to swap the boards over because things get really interesting when I move the double bond. Okay, this one here is an example of butene. Got 4 carbons, and if I number them in this one, 1, 2, 3, 4, it doesn't matter which way I number it, you'll see that the double bond is on carbon number 2. So this is butene. Sadly, that won't get you a lot in any assessment because it doesn't quite describe it well enough. And these are the ones I recommend you make with the models to see that I'm telling the truth. Because a double bond does not allow for the rotation of the carbon atom, okay, it's too rigid, it won't allow for the rotation, then actually these carbons either get held in place opposite each other through the double bond, or they get held in place on the same side or together. And when we condense these structural formulae, they look like this. You'll notice I'm still showing some carbon-hydrogen bonds in the condensed form of it. Alright, and that's to show the actual geometric arrangement. So these are called geometric isomers. They both have the same thing, CH3, CH, CH, CH3, but if I actually make them out of models and therefore look at the shape of their electron clouds, they actually look different. They have slightly different properties if they have polar groups on these. Right? These two have very similar properties, but you can almost tell, because the electron cloud size is here, it'll be quite hard to pack these in tightly together, because they've got quite a big side and quite a small side. Because these ones might be easier to pack together, because of the way they're arranged. Alright, well, how do we name these? They're a little bit, well actually, I don't know, I find them quite easy. Once you know the rules. Trans means to go across. That prefix means to go across. So in chemistry we use it. The carbon chain goes across the double bond here. Can you see that? It's going across the double bond. Alright, if I try to connect the 2 carbons together, I have to go across the double bond. I'm just going to redo that quickly. Tidy it up. So if I draw a line between the 2 carbons, it goes across the double bond. Can you see that? So it goes across. It transits the double bond, or transcends it. So we call this trans butene. Let's got a hyphen. Not that it's that important. Okay, so that's trans butene. That one's not needed. Alright? And this one here, if I join them, okay, and if I try to go through the others, makes the letter C. Okay? C is joining them. There's a way I used to remember it. The letter C is joining those 2. And this one's name is cis. U, 2, and C is joining the carbon chains. Alright? So there's a little bit more to their names, and these are called geometric isomers. The importance is that sometimes they have different densities. If they've got polar groups on them, it can change their polarity. So the dipoles can cancel out with trans that don't normally cancel out with cis and so on. So that's the importance of this. And that's why we need to learn them. There's one more thing I wanted to mention, but I've forgotten it, so it can't have been important. Right, I will write up there that these are called geometric isomers. Alright, and there we go. So, just to recap, we've looked at naming them. They all end in E and E. If the double bond can be put in different places, you have to put a number there to say which carbon it's on. Once you get to 4 carbons, if that double bond is in the middle somewhere, then it's probably likely you're going to get cis and trans or geometric isomerism. So you need to know how to name those as cis or trans. And the reason for that is because the double bond is a lot more rigid than a carbon-carbon single bond, which will allow for free rotation. There is no free rotation of this, so they can't be turned into each other without being an intermediate compound first.